Good morning, everyone. How y'all doing? All right. Today is Friday. Today we're going to practice a bit more 2D motion vector addition, and then we'll be done with chapter 3. How do you guys feel? And does anyone have any questions, needs, concerns, etc. before we get started?
Are you going to post our lab on Brightspace, or do you have it when we come? Or?
Yes, you don't have to prep or bring anything
Okay.
with you. It's there in the lab. Yeah, you don't have to. The lab is entirely contained within lab. There's nothing you have to prep before time, and there's nothing you have to do after the fact.
Yeah, it's not like that in our biology courses. There's like pre-labs, calculations, a lot.
Yikes. Well, this isn't the bio department. Anything else on your minds for here at the start? All right. Now, we have been talking about 2D motion and how to use trigonometry to help us add two-dimensional vectors together. We're going to look at a few more examples of that today, so that make sure everyone feels comfortable with it before we move on and start looking at new types of vectors next week. To kind of preface next week, we're going to begin studying Newton's laws of motion, primarily force, which is a new vector that we will be adding two-dimensionally. So we'll practice with the ones we've already done before we add that one to the list. To add vectors, you want to make sure to draw a good picture, drawing the vectors you're adding together tip to tail to kind of demonstrate how the overall motion combines together. And then you want to add specifically x with x and y with y. We've mostly been practicing doing that with x and y vectors, in which case you just have to note which axis the vector is in. But today we're going to start off by adding two vectors that are not entirely x or y. This means, in order to add these together, you have to break them down into their component forms first. So the two vectors we have here, let's say that this is like a hiking trip or a jog. Someone's going to move 20 meters at 40 degrees above the x-axis. And then, once they get there, they're going to switch directions and move 40 meters at 25 degrees above the negative x-axis. And so from start to finish, they begin here and they end up here after these two different motions get added together. So we want to determine the vector displacement from start to finish. That is the vector that points from here to here. And in order to do that, to add these vectors together, we have to first break them down, make sure we are adding x with x and y with y. So, try to color code this. First, we've got 20 meters pointing at 40 degrees. How do we find the xy components of this vector? We've got, well, we started with just the vector itself, 20 meters pointing in this direction, and that is a vector, magnitude and direction. We need to break that down into its components, and I always recommend turning your vectors into a right triangle in this class. We're going to describe pretty much everything as a right triangle. The y leg, vertical leg being y-axis, horizontal leg being x-axis. Those are conveniently always 90 degrees apart, so we have a right triangle, and that means we can use SOHCAHTOA. So I'll just write that up here for review's sake. So, we need to find both the y and x legs of this triangle. In comparison to this 40-degree angle is the x leg here. Call that, yeah, we'll just call that x1. Is this x leg adjacent or opposite the 40 degrees? Very good. Rules for adjacent are that it is touching the relevant angle, but it is not the hypotenuse. The slanted one is always the hypotenuse. So that's going to make this the adjacent leg, and by process of elimination, this will be, the y leg will be opposite. So for this triangle, we know the hypotenuse, we know theta, and we want the two legs. So we just have to pick at least two of these trig functions to help us find those two legs. Tangent's not going to really help us here because TOA stands for tangent is opposite over adjacent. We don't know either of them. So TOA is not going to help us initially. So I'm going to direct our attention to sine and cosine instead. Sine says sine of theta equals the opposite leg over the hypotenuse. So sine of 40 degrees. We already said that our opposite is going to be y and our hypotenuse is 20. So that will determine the y leg for us. And cosine stands for cosine of theta equals adjacent leg over our hypotenuse. So those two will help us figure out our legs in this scenario. Please let me know what numbers you determined for those as you counted.
For sine, I got 12.8.
Fantastic. I'm going to round that up to 12.9, but yes.
And for cosine, I got 15.3.
Fantastic. Any questions or issues arriving at these dimensions? All right. I've also noted what direction these point in, because that will become relevant as we continue on. So that is the first triangle completely divided up. We now know all of its sides, XY components, and we'll be able to use them once we also know this triangle's XY components. So, just have to do the same thing to the blue one. Which, the legs are different sizes, but the orientation of the triangle is the same, if only mirrored. So from this angle's perspective, its x leg should also be adjacent, and its y leg should also be opposite. So I'm just going to use green and label those as x2 and y2 for the second vector. And since x is still adjacent and y is still opposite, the same trig functions should help us here. You just want to make sure to plug in the new numbers for the second triangle. So I'm going to take these and repurpose them over here. Sine is opposite over hypotenuse. Opposite is still going to be y for this one. So sine of this triangle is 25 degrees. It's going to be y2 over our new hypotenuse of 40. Meanwhile, cosine of 25 will be x2 over the new hypotenuse of 40. How's that feel?
y2, I got 16.9.
Fantastic. That leg points up.
And for x2, I got 18.1.
18.1?
Yeah.
I pause because that's not what I have.
Try again.
I defined x2, that should be equal to 40 times cosine of 25 degrees.
Oh, yeah, I'm sorry, 36.25.
That is what I got. Does anyone disagree? Okay. Questions, comments, concerns? All right. So, with all that done, we have now divided up our two vectors into all of their relevant components. After doing that, we can now begin the process of actually adding the vectors by adding x with x and y with y. So, I'm going to take the components and use them to write each vector out in component form. Assuming that the red one is vector number 1, that's going to be 15.3 for its x and 12.9 for its y. Vector 2, we got 36.3 for its x and 36.3, yeah, and 16.9 for its y. Are we good to go? Has anyone caught the mistake that I left in on purpose? One of the x's should be negative. Because if you look at this picture, the two x legs of these two different triangles work against one another. One points left, one points right. Now, the thing about your calculator, if I haven't said this yet, smart calculators are still really, really dumb. Your calculator does not understand the broader context of the trig functions that you are putting into it. Because unless you do something very specific, your calculator doesn't necessarily know that this x answer arbitrarily points in the opposite direction as this x answer. So your calculator lacks that context. Your calculator is going to give you two positive numbers for each. But we, the beings with creative brains, are able to look at this and know that they work against each other. And so our calculators won't do it for us. We have to be the ones to put a negative sign somewhere here to make this make sense. Because if we just add these two numbers together, that's not really going to represent what's happening here. If we proceed with this as it's currently written, we're going to get a really big positive x answer and the correct y answer. If we do not add a negative sign here, then we're going to get a big positive x answer, but we're supposed to get a negative x answer. We know the answer is supposed to be negative x, because if I do actually draw in the final vector, so from start to finish, this is the vector we're trying to find, is that dotted line. It still points in the negative x direction, right? If this is our origin and we assume on a traditional Cartesian plane, left is negative x, right? And this vector, this sum that we're trying to find, points to the left in terms of the x-axis. So we should be expecting a negative x answer, which we don't get if we don't add this in ourselves. That's why pictures are very important, and it's why thinking about what the numbers in the situation physically represents is important. Because if you just treat this class as a number crunching operation, if you just think of it as pure math and don't look at the logic of the physical situation, you're going to get situations where your calculator doesn't know something's supposed to be negative, and if you don't add it in yourselves, your math stops working. Yes?
So we can practically fill out like where it goes, and if it goes to the left, our x should always be negative, and if it goes to the right, it should always be positive.
Yes.
What about the y, which way?
Well, in this specific case, our two y's both point up. So they do not work against each other. They work together and add up normally in this scenario. But if we were adding, say, this vector to this vector, here the y's work against each other, and one of them would have to be negative.
So the y is negative if it's going to the right?
Y is negative if it points down. Sorry.
Okay.
So yeah, if these were, if instead of this question, if we were instead doing one like this, this would be two right-facing x's, but one y points up and the other points down. So in this scenario, we have two positive x's and then one positive y and one negative y. So drawing your picture is always very important, especially marking more lines on top of the picture. If I give you a picture, write all over on top of it. If I give you a picture on a test, I'm encouraging you to doodle all over the place. Did I answer the question?
Yes, absolutely.
Any other concerns, opinions, etc.? All right. So, calculator can't tell you this negative yourself. We have to add it in. Calculator can't tell you this negative. We have to add it in ourselves. And it's usually why when I'm writing things out like this, I especially make note of what direction vectors point in. So, the x leg of vector 2 points in the negative x direction. We're adding that negative in ourselves. And that is going to give us negative 36.3 minus 15.3. Oh, sorry, plus 15.3. It's going to give us negative 21 in the x and 29.8 in the y. Positive 29.8, because both of the y legs point outwards. And so that's the component form of our final answer. That's meant to tell us, I don't have a blue marker, so I'm going to use green in place of blue. If we're adding these two vectors together, from start to finish, the final summation vector should have an x leg of 21 pointing left instead of right, and a y leg of 29.8. How's that feel? Now, my pictures often are not totally to scale in here. I am not an artist. Most physicists aren't, unfortunately. But in an attempt to make this roughly to scale, I'm hoping to demonstrate that these numbers kind of make sense to the rough geometry of the picture. We're slightly to the left and then slightly more up than we began. So these would be the coordinate locations that we end up at in comparison to, say, an origin point of 0. So that's the component form of our final answer. Feel good? All right. Now, that's not the only way to write a vector. So last thing that I'd like to do for this specific question is, what would the magnitude and direction form of this answer be? What is basically the hypotenuse of this triangle and the angle that it points at?
Can we like do the square?
Yes, we can. What's the name of that rule? I think someone just said it. Pythagorean theorem. Very good. Which letter in this theorem is always hypotenuse? C. Very good. And conveniently, if we keep our negative pointing x-axis vector negative, the squared in the formula kind of gets rid of it for us, which is nice. Means that we don't end up taking the square root of the negative. So, what is the hypotenuse of this triangle? Bless you. Very good. And since that's not necessarily in the x nor y axis, we don't really need to put a negative on it. Instead, the angle specifies what direction it points in. So that's the magnitude of our final summation vector. So the straight line distance between your starting point and your ending point. So what is that theta then? What is that unknown angle?
Can we use tangent?
We can use tangent. Technically, you could use any of the three trig functions you want here, since you have all three sides of the triangle. But I like tangent because we don't use it that much, and we started with these two sides, so it makes the most sense to me. That means you could, find this in any order. So tangent of our mystery angle. Tangent is TOA, opposite over adjacent. So we just remind ourselves quickly. From this angle's perspective, y would be opposite and x is adjacent. And remember, your calculator doesn't actually have any context for positive, negative vectors, what direction things are pointing in, because your calculator is not looking at this and knowing that intrinsically. So if we put this negative facing x vector in here, it'll give us an answer, and it may have a negative sign, but the calculator doesn't really know what that negative means. I'm going to put the negative on so we see what happens. I'll elaborate on what it represents. But note again, this thing is real dumb. It doesn't see the picture. It doesn't quite understand what all the directions actually mean. We have to interpret that meaning for ourselves. So theta should equal inverse tangent of 29.8 over negative 21. So what angles do you guys get?
54.8.
Very good. Now my calculator gave me a negative because I kept the negative on the x leg. So I'm going to write that negative down just to elaborate on what it means. So the magnitude and direction form of our final vector is 36.5 meters at 40, sometimes the letters just come out in the wrong order. The numbers come out in the wrong order, I apologize. 36.5 meters at 54.8 degrees. And when I put specifically 29.8 over negative 21 into my calculator, it gave me negative 54.8. No wrong answer, but if you can recall from previous geometry classes, what might that negative mean if we interpret it literally?
It's in the third quadrant?
Kind of. Well, for one, this vector actually points into the second quadrant. If you haven't had geometry in a while, what I mean by quadrants is this standard sort of graph, we call this a Cartesian coordinate plane, but it's kind of just the standard graph you've worked with before. It's divided up into 4 sectors, and we call those the 4 quadrants. And they're numbered counterclockwise 1 through 4, starting at positive x. So you're usually operating in the first quadrant, the way most graphs are drawn, but this vector actually points in the second quadrant. And you are kind of correct. It's not the way I describe it, but you're getting to the right point. This vector is in the second quadrant. It's not necessarily in the frame of reference that we normally operate from in a standard sort of geometry class. This negative angle means that we've drawn this triangle in such a way that theta is going clockwise, when most geometry does angles counterclockwise. Again, if you haven't had many geometry classes lately, it's okay if this isn't ringing bells. This is maybe review, maybe the first time you're hearing it. But most mathematicians, if they're operating from a plane like this, they tend to start everything from positive x and then rotate counterclockwise around from there. And if angles are meant to start here and go clockwise, this one kind of breaks the mold in 2 different ways, because 1, it points normal clockwise, and 2, it's not starting from the perspective of positive x, it's starting from negative x. So the negative number for an angle means clockwise instead of counterclockwise. And again, I'm talking about what mathematicians normally do, because that's the way your calculator is programmed to think about it. Calculator was programmed by mathematicians, and it's not able to deviate from that norm. So when it gives you that negative angle, it's because the calculator thinks this is drawn to point clockwise, and it is in this case. But this number is specifically clockwise away from negative x, which is just not the way most mathematicians write their answers. So the ultimate point that I'm trying to make here is, when writing down the direction that a vector points, sometimes you have to be really specific about your frame of reference. This number is a correct answer for this picture. Like the way we've drawn this picture, this is the angle that fits right here. But if you were trying to tell a physicist or a mathematician this answer without the context of the image, you have to be very specific about what frame of reference this angle is from. Because this is a clockwise angle from the negative x-axis, which again is just ways that mathematicians don't normally write their angles. So this is a lot of words for me to try to compress down a point into. When writing down an angle answer for magnitude and direction of a vector, you want to try to be very specific about what direction that angle points in. Because if you just write an angle by itself, if all we did was write 54.8 degrees as your final answer, someone reading that might assume, all right, I start at the x-axis and then I turn that many degrees counterclockwise from x, which is the mirror image of what's happening here. Because this is just what most mathematicians do based on textbook. So to make sure that your answer is as right as possible, and to make sure that it is as clearly interpreted as possible, you usually want to add a few qualifiers to it. In this particular case, I could describe this as 54.8 degrees above negative x, because it is specifically tilting upwards from the negative x-axis, as opposed to tilting upwards from positive x. So that's just a qualifier to make sure that the direction is interpreted correctly by whoever's reading it. Bless you. I want to point this out because sometimes the questions that you will see in this class between homework and tests will tell you vectors, it'll give you qualifiers in the opening statement, and you have to be able to interpret them correctly. So what this qualifier means is degrees above negative x. You start in the negative x-axis, and then you tilt this many degrees up from it. Like physically, literally upwards. How does that feel? Yes?
I'm confused, like in the football example, how we had zeros in there and we don't in this one. Like how, I don't understand how to tell if x or y is zero.
Oh, so, thank you for asking. I'm just putting this down so that the words aren't interrupted by a bunch of math. Where is the football? Here we go. I've changed the wording slightly, if it disagrees with what you've already written down.
Yeah.
No, that's not the one. This is a different question, sorry. Here we go.
Yeah.
Sorry, apologies. I've changed the wording on this one too. I've got too many things in my notes. So we did this one on Wednesday, correct? All right. Now in this case, the vectors being given here are all straight lines within single axes. So it said the person starts at origin, runs backwards in the negative x, then upwards in positive y, and then forwards in positive x. Those numbers being 10, 15, and 50. So these are also vectors that all needed added together, and technically the process of the question we just did and this are the same. The only difference is these vectors all point at angles and they are not fully in either the x or y axis. So every single vector here has both x and y components that all need divvied up and properly added together. But in this scenario, each of these vectors is only in the x or y axis. And so, like when you run specifically just backwards along the negative x axis, this 10 yards is entirely in the negative x. It didn't need dividing up. You could consider if I was to give you a magnitude and direction for that vector, it would be 10 yards pointing in the negative x direction at 0 degrees, because it is along the axis itself. Angle is 0. And when the angle is 0, you're entirely x-axis with nothing in the y. So these are technically two-dimensional vectors. It's just, if I write them out in full 2D vector form, they each have an opposite component of 0, because they point very specifically within single axes. They don't have angles that require you to divide things up into components. Did I answer the question?
Yes, that makes
Okay.
a lot more sense.
So, when looking at the question, it is important to note if it has an angle or if it's just pointing within a single solid line. Because if it's in a normal axis, you don't have to do any trig yet. You can just assume if something points in the x, its y component is 0. If it only points in the x, its y component is 0, and vice versa. If it only points in the y, its x component is 0. Sound okay? All right. So. Any other questions about all this stuff we just did? Okay. Now, that's most of the lecture done. I don't want to start a new big long example when there's less than 10 minutes left, and I don't want to hold you up on a Friday. So very quickly, the last main thing that I want to do with you guys I want to demonstrate and practice a little bit more what I mean by adding qualifying statements to your angle measurements. So I'm just going to draw very arbitrarily a few different vectors . That all points in very different directions. And I just want us to think about what frame of reference each of these angles is from, how you would best describe the directions these things point. Here we have something pointing at 30 degrees. What is that 30 degrees from? Above the x-axis. As a result, we're starting at normal positive x and tilting literally upwards from there. I would think to describe this as 30 degrees above positive x. Now, most mathematicians assume this is the norm, if I'm being honest. Tilting above positive x is normal. And so, frankly, if you just didn't write that, most mathematicians would assume that automatically. But I also want to add in a different frame of reference option, because a lot of questions, rather than positive x and y, use compass orientation, north, south, east, west. So to make sure you're familiar with that version as well, instead of positive x, you can describe that as the east axis, and instead of above, it's tilting towards north. So an equally valid way someone might write this is 30 degrees north of east. That's what that means if it shows up in a homework question. Blank of blank means you start in the second axis and then tilt towards the first one. North of east means you start east and tilt towards north. Keeping that in mind, how would you write this one? All right, so 25 degrees above, well.
North of south, I guess?
Sorry, you guys are making good guesses, but you're giving like both versions simultaneously, so my brain just having to pick through them all. It's 25 degrees. What axis does it start from? Positive y. So 25 degrees, you could call that from positive y, or rather counterclockwise from positive y. But if we were using north, south, east, west instead, we're starting from north and tilting where? West. So you can alternatively say 25 degrees west of, I almost wrote east, west of north. So you have to determine where it's starting from and then where it's tilting. And it's always starting from, usually I add a dotted line to represent the original axis and then the angles, the degrees tilted away from there. So, figure out what axis it's from the initial reference point of, and then what direction it tilts from there. How about this one? Just south, or negative y. You could also call that, if you really wanted to be fancy, 270 degrees from positive x. But that's just splitting hairs. How about this last one?
Degrees south of west.
Very good. South of west. Starts west, and then you tilt towards the southern axis. Just to give another example, someone might also call this 75 degrees below negative x. How do you guys feel? Okay, I'm glad to hear that. I wanted to address it because some people, if I don't address it and then you start seeing it in homework, a lot of people usually have questions. So, if this sort of description system is ever confusing to you, please let me know. I'll make sure you understand what direction things point in. And that'll be it for today. Next week we begin force and Newton's laws of motion, which I guarantee you've all seen before. Let me know if you have any questions, and have a wonderful weekend. Oh, like, you mean just from?
Yeah.
Ah, yes, I apologize. The normal assumption, normal for this is counterclockwise.
Okay.
So a positive angle without specifying anything else is always assumed counterclockwise.
Okay.
Apologies.
Alright, no, you're good. I was just wondering, like.
That's why I usually prefer the direction of direction, because it removes that added ambiguity.
Okay.
So I like to use blank of blank.
Okay.
So that's what I'm gonna stick to for the most part.
Okay, thank you.
You're welcome. This is out of order. No, it's not. Camera.